Okay, so this video is going to be over Thermodynamics 2C, and this section is related to solving problems using specific heat and calorimetry, what I call two-object problems. Okay, so in past sections, we kind of talked about the difference between thermal energy and temperature. Okay, so thermal energy is the total kinetic energy of all the atoms or molecules making up an object, whereas temperature is a measure of the average kinetic energy of all the atoms or molecules making up an object. Now, if all substances were the same, we wouldn't need this distinction between thermal energy and temperature. Okay, but we did some examples in past videos where we were looking at two objects, I think, like where they had the same temperature. That means they had the same average kinetic energy, but different amounts of thermal energy because one had more atoms than the other. Okay, and so the way we make this distinction between how different materials react differently with heat has to do with what's called specific heat. So when let's talk about specific heat. When energy, that is, when heat flows into a substance, the amount of temperature gain is dependent on the properties of the substance. We all know just from experience that some things heat up faster than other things. Okay, for example, metals tend to heat up very fast. Now, not all substances transfer heat at the same rate, and so this brings up the idea of what's called specific heat. The specific heat of a substance is the amount of heat needed to increase 1 kilogram of a substance by 1 degree Kelvin, or 1 degree Celsius. Okay, now for reasons I don't understand, the symbol for specific heat is a C. And if you look at the definition, the amount of heat needed to increase 1 kilogram by 1 degree, basically what that means is specific heat is a number that basically quantifies how easily a material changes temperature. Okay, now we have a calculation with specific, we have an equation with specific heat that we will see on the next slide, but that's basically the concept of specific heat. Okay, so pause it there if you need to look at that some more. And let's look at our equation for specific heat. And you might have even seen this equation before, or maybe not. The equation for specific heat that we will be solving problems with looks like this. And it is Q equals mc delta T. Okay. Now Q, we've seen Q before, that is heat. Either heat gained or heat lost if you have a negative Q. Okay, so you can have negative heat. That just means you're losing heat instead of gaining heat. Okay, so we've seen Q before. Mass, we've seen that before. Okay, that's the measure of the amount of matter making up an object measured in kilograms. C is specific heat. Now again, I don't know why we use C for specific heat, but we do. And it does have units, but the units are kind of complicated to explain, so let's not worry about the units for specific heat. And then finally we have delta T. Okay, you've probably seen this triangle before. Hopefully you've seen this triangle before. This is the Greek letter delta, and delta represents a change in. Okay, so for example, in algebra you might have seen delta y divided by delta x, change in y over change in x. In this context, delta T represents change in temperature. Now, anytime you ever see a delta in math or science, it always means change in, and that always means final minus initial. Okay, this is something really important that you need to understand. This is not delta times T. This whole thing is delta T. Okay, that means this whole thing is the final temperature minus the initial temperature. Okay, make sure you don't get this switched around. Okay, so Q equals mc delta T. And this equation basically lets us do calculations, based off of, when we add heat to an object and how does the specific heat affect the temperature change. Okay, so pause it there if you need to write the equation down. And let's take a look at some problems. Okay, now before we get to some examples, I want to show you this chart of specific heat values. It's very common to be given a chart on these problems because you're not expected to memorize different values of specific heat. I know I don't. And so this chart has just some different specific heat values for different materials. Okay. Again, the higher the specific heat, basically that means that the more heat it takes to raise the temperature of that object. So in other words, the higher the specific heat, the more difficult it is for that substance to change temperatures. So for example, if you're looking at this chart, if you add heat, let's say you add, I don't know, 100 joules of heat to a piece of lead and 100 joules of heat to a piece of glass, and they have the same mass, the lead is going to increase in temperature more than the glass because it has a lower specific heat value. Okay, so higher specific heat, more difficult to change temperature. If you look at this chart, you'll see that liquid water has a specific heat value of about 4,180 joules, or not joules, but in whatever the units are, joules per kilogram Kelvin. Water actually has a very high specific heat. It has one of the highest specific heat values out there, which means that water really does not change its temperature very easily. Okay, it takes a long time to heat up, and it takes a long time to cool off. Okay, which is good because otherwise the oceans would change their temperature every single day, and they would fluctuate widely and cause massive storms all over the planet, and that would be bad for us. Okay, so let's look at some calculation examples with this chart. Example 1 says, how much heat must be added to a 50 kilogram sample of lead to increase its temperature by 100 degrees Celsius? Now, first things first, we have the given, how much heat. Remember, the symbol for heat is Q. Okay, so that is what we're trying to find. We're given the mass is 50 kilograms. We're told that it's lead. Now, because it's lead, we can look over here to the chart, find the specific heat value for lead, and that's going to be our C. And then we're told that the increase in temperature is 100 degrees Celsius. So Q equals mc delta T. In this case, we're looking for Q, so all we have to do is plug in everything else. The C for lead is 130, and the change in temperature it says in the problem is 100. Okay, notice I'm using the specific heat value for lead. That means if I changed it from lead to copper, it would be 50 times 385 times 100. But because it's lead, I use the specific heat value for lead that's in the chart. Okay, so I get my calculator and I multiply these things out. Okay, let me do that really quickly. Okay, 50 times 130 times 100. And remember that heat is measured in joules. So I get 650,000 joules of heat, and that is the answer to example 1. Okay, very, very basic calculation with specific heat. So pause it there if you need to look at that some more. Okay, next example. Example 2 says how much heat is released when a 0.45 kilogram piece of aluminum cools from 45 degrees Celsius to 15 degrees Celsius. So now there's a little bit more going on here. So if you look at the question, how much heat, the unknown is still Q. Okay, so that's what we're solving for. By the way, if heat is being released, that means Q should be negative. Just keep that in mind. We are given the mass, 0.45 kilograms. We're told that it is aluminum, which means I need to look over here at my chart. There's a specific heat value for aluminum, 903, so that's going to be my C. And then look at the temperature. Okay, we're given two different temperatures because remember in the equation, we don't actually have temperature in the equation, we have change in temperature. Because the equation is Q equals mc delta T. And delta T, again, change in temperature means the final temperature minus the initial temperature. So we need to identify which one is which. Well, if it's cooling from 45 degrees Celsius, that means the 45 is the starting temperature. I'm going to label that Ti for the initial temperature. And I'm going to label the 15 degrees Celsius Tf for final temperature. So when I go to plug in for Q, watch what I do. I plug in the mass, 0.45. I plug in C, which is 903, and then for delta T, I plug in T final minus T initial. So I'm going to do parentheses 15 minus 45, close parentheses. These things are all being multiplied together, but because they're in parentheses, you have to make sure you do the subtraction first. Okay, so I'm going to type that in. Okay, 0.45 times 903 times 15 minus 45, and I get negative 12,190.5 joules. Notice, by the way, that my Q did turn out to be negative, just like I predicted. Okay, that's because my change in temperature was negative, because I went down in temperature. So, of course, heat was being released. Okay, so pause there if you need to take a look at that. Okay, so we're going to do a few more examples. Example 3 says when 5,000 joules of heat, notice by the way here, heat is Q, we're actually given Q, okay, so that's a little different, is added to a glass bowl. Immediately I'm looking at my chart, I'm saying here's a glass, 664, that's going to be my specific heat, that's my value for C. And it says the temperature of the bowl changes from 24.5 degrees Celsius, that's my initial temperature, to 30.2 degrees Celsius, that's my final temperature. Calculate the mass of the bowl. So now mass is my unknown. I'm still using the same equation, but now I need to do a little bit of algebra to rearrange. I take my equation and I plug in my givens. Q is 5,000 joules. The mass is unknown, so I leave that in there, but it's being multiplied by 664, and then it's being multiplied by delta T, which is final minus initial. Okay, the final is 30.2 minus the initial is 24.5, and there we go. Now, before I solve for mass, I'm going to simplify. Okay, I leave the mass alone, but this times this, I can actually simplify that. So first I do the subtraction because of PEMDAS. Okay, don't forget your order of operations. You have to do the subtraction inside the parentheses first. And I get 5.7, and I multiply that by 664. Okay, so the mass is being multiplied by 3,784.8. Okay, I just simplified right here. Now I want to solve for mass, so I say what's being done to the mass? Well, it's being multiplied by this number, so to undo that multiplication I need to divide both sides by 3,784.8. So I'm going to do that now. My calculator, okay, that cancels, and I will put my answer up here. The mass is going to be, let's see, 1.32 kilograms. So I'm just going to write my answer to 2 decimal places. Okay, so that is example 3. Same equation, not really anything different other than now we actually have to do algebra to rearrange the equation. Okay, so pause it there to take a look at that some more. Okay, so I'm going to do 1 or 2 more examples. Let's see, example 4. Okay, actually, before we do example 4, let's see. Actually, I'm going to switch these two. I'm actually going to make this example 4, and I'm going to make this one example 5, just because it's a little bit more challenging. Okay, so example 4 says a 1 kilogram amount of each of the materials shown to the right are placed on separate hot plates at 0 degrees Celsius and heated for the same amount of time. Explain which object will reach 100 degrees Celsius the fastest. Now this is a concept question. We talked at the beginning of the video about the concept of specific heat. The object that's going to reach 100 degrees Celsius the fastest is going to be the one that heats up the easiest. So which one heats up the easiest? Well, that's going to be lead, because lead has the lowest specific heat value. Okay, so that is going to be the 1 kilogram piece of lead. Now, which object is going to reach 100 degrees Celsius the slowest? That's going to be the object that has the highest specific heat, right, which would be the liquid water. Remember, water has a very high value for specific heat. Okay, so that is example 4. No calculations involved. That's just a concept question. Now, if you do like math and you want to think of it in a more math way, think about it like this. The equation is Q equals mc delta T. And this problem is basically saying they all have the same mass, they all have the same change in temperature because they're going from 0 to 100. So that means the only difference between all of them is C. Okay? And so you're going to have the most heat if you have the biggest C value. Okay, so the liquid water is going to take the most heat to increase the same amount of temperature. Okay, so we're going to do one more calculation question, and then we will be done. Okay, and this calculation question we're about to do is probably the most challenging one. Okay, so follow along closely. Okay, example 5 says 5.6 times 10 to the 8 joules is used to heat a hot tub which contains about 5,000 kilograms of water. Now, if you don't know what this number is, 5.6 times 10 to the 8, that is basically 560 million joules. Okay, if you prefer to write it as 560 million joules, then you're welcome to do so. Okay, so I will just write 560 million joules. Okay, like that, is used to heat a hot tub which contains about 5,000 kilograms of water. Okay, so there's the mass. This was my heat. Okay, look at the unit, it's in joules. If the water initially has a temperature of 25 degrees Celsius, so they give me the initial temperature, calculate the final temperature of the water. Okay, so same equation, but now my unknown is T final. And this is definitely going to take the most algebra out of all the problems we've done. Okay, so let's start by writing the equation and plugging in what we know. Now I know Q is, I'm just going to write it in scientific notation just to save on space, 5.6 times 10 to the 8. If you are not familiar with scientific notation and you want to write it as this big number on your paper, go right ahead. I just have limited space on my screen. We know the mass is 5,000. I'm putting parentheses to remind myself I need to multiply. The specific heat of water is 4180. And now, I don't know what delta T is, okay? But remember that delta T is T final minus T initial, because change in temperature is always final minus initial. So I'm going to plug in final minus initial temperature, okay, for delta T in the equation. I don't know the final temperature, so I leave that in, but I do know the initial temperature is 25 degrees, just like this. Okay, so I'm going to have to do some algebra to get T final by itself. Notice that T final is actually stuck inside parentheses. Okay, so you have to be really careful with what you do first. You might look at that and be like, oh, I'm subtracting 25, so I have to add 25. No, you can't add the 25 because the T final minus 25 is inside parentheses. Remember, when you solve for something, you have to do PEMDAS backwards, and parentheses is, the very first thing in PEMDAS. Okay, so what I'm going to do first is I'm going to simplify the 5,000 times the 4180. And so let's see, 5,000 times 4180 is a big old number. Okay, so I'm going to simplify it down here. 5.6 times 10 to the 8 equals this big old number right here times T final minus 25. Okay, so I want T final by itself. This minus 25 is stuck inside parentheses, so I can't deal with that yet. I need to start by dividing both sides by this big ol' honking number right here. Okay, so I'm going to do that. Okay, and I'm going to just type that into my calculator because I don't want to try to do that without a calculator. And the value I get is 26.8. Okay, I get 26.79. I'm just going to round that to 8 equals T final minus 25. Okay, so now my last step, what's being done to T final? Well, it's being subtracted by 25. I can get rid of the parentheses because everything else is gone now. And so now I just need to add 25 to both sides. At plus 25 plus 25. And when I do that, 26.8 plus 25, I get 51.8 degrees Celsius. And that is the answer to my question. So you see, specific heat calculations by themselves are not super difficult, but based off of the information you're given and based off of what I'm asking you to solve for, the algebra involved can be kind of challenging. Okay, so but concept-wise, all of these examples are the same. It's the same equation. You set it up the same. It's just you rearrange it differently depending on what you're trying to find. So hopefully you feel a little more comfortable with specific heat and you can work on your practice problems with specific heat before the quiz. Please let me know if you have any questions, and as always, I will see you guys in the next video.